go from current slide. All right. I think I said this announcement before, but just to remind you and get it on the Screencast-O-Matic, which will go to YouTube later. The good news, bad news situation, you know, right? Good news is next week is Thanksgiving. Thursday and Friday are state holidays. The college is closed completely, okay? But the bad news is there's no classes at all next week, okay? So you don't come at all next week. We have professional meetings. A few people are going down to Mobile for the state Alabama Community College Association or system meetings. They start Sunday evening and they go Monday and Tuesday, and then Wednesday's a day to drive back. But for those of us who don't go, we have professional meetings on the Birmingham West campus, and they will be Monday and Tuesday, basically pretty much all day long. And then on Wednesday, I think they'll usually give us an office day, so I'll be in the office that day. So a couple of issues with that. Number one, if you have any business to do with the school, there's certainly no classes, so don't come for classes. But if you do have any business to do with the college that you need to take care of, you can do that anytime Monday, anytime Tuesday, okay? Or Wednesday morning, okay? Anytime Wednesday morning. Now, the reason I say that, though it's not guaranteed, most times they'll give us some time off on Wednesday afternoon, the day before the big holiday. But that's not guaranteed, so we don't know that they're going to do that. But usually it's 12, 1, 2 o'clock, something like that. They'll say, okay, y'all can go home. They never tell us ahead of time. They never tell us until when they decide to. So I can't say when the offices will close, but they will. Now, the offices won't be fully staffed because some people may be down at the meeting, some people may be taking personal leave or something like that, but someone will be in all offices Monday, Tuesday, and sometime on Wednesday. I just can't say when on Wednesday. Okay, that's that. Faculty, however, will be in the meetings, so we won't be available Monday or Tuesday, but we are available on Wednesday, and I hope to be in my office here on Bessemer campus. But if something comes up during the meetings that I find out I have to be on the Birmingham campus, I'll be at that office. So I would suggest if you do need to contact me on Wednesday morning, try to do so by phone first to find out which campus I'm located. And if you don't get me by phone, wait a few minutes and try again, because I may be out in the restroom or having to run down to an office somewhere. So give me a few minutes, try again. I'll be around the office sometime Wednesday morning and probably into the afternoon, but at some point when they let us go, I'll be out of there. Okay, so that's what's happening next week. Then we come back after Thanksgiving. And does anyone happen to know right off the top, is it December 13th either during finals or after finals? Does anyone know that schedule? During finals, okay. Because my wife found out yesterday she's going to have a procedure that day, an outpatient procedure. That means I have to drive her to the procedure, stay there until they're through with the procedure, and drive her home. So there's a real good chance I won't be on campus at all that day, the 13th. On top of everything else, it's her birthday, and she's having to have a fairly major procedure done. But she'd rather that with her doctor than have it by somebody else. So she made that call. All right, but just to let you know ahead of time. And if that is indeed, and I think it is finals week, I'll let you know what the deadlines are, but normally that would have been a day I'd say you could turn in your last test, final exam. Actually, we'll probably have both the last test and the final due that day, or due that week. So you could bring it those days, but I probably won't be here, so just slide it under my door. Otherwise, you can give it to me in person if it's another day. Okay. Now, that said, any questions on what we've done so far? Okay, everybody, let's see, let me look and see this. How many have done their research paper? Oh, one. Okay. My best class ever, of course, and only one person doing a research paper. That's a little slack. We only have a few weeks left. Okay, as in, yeah. A little time in November, and then the rest is December. November gets you the bonus point. December, no bonus points. Okay, test one. I'm preaching to the choir here, but I've got 3 people that have not turned in test one. The rest of you have good. Test two. I think I got the first one in today, so please be working on those. And all of you hopefully have your test 3 already too, so be working on that as well. And we're closing in on test 4, not immediate, but closing in on it here. So here we are in example 1 on page 409, Miracle Formula 409, okay. Chapter 6 is additional topics in trigonometry. 6.2 is law of cosines. So we talked about what the law of cosine was, and not doing that. And here is example 1. And if my memory's right, we got started on this one, right? You think we finished it?
I stayed after class.
Say again?
I stayed after class and we finished it.
My hearing's bad. One more time.
So we finished it after class.
Oh, after class. Okay. 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 So what we did, if my memory's right, and this will just be a little bit of review, what you always go for when you have the 3 sides given and you're wanting to determine angles, what's the rule? Yeah. Well, no, it's law of cosines, okay? That's the rule, okay? That's the law that you use. But in using the law of cosines, which angle do you go for first? If you're looking for all 3 angles, always go for the largest angle first. You got the 3 sides, find the longest side, and you're going for that angle right opposite in. And here's Walter. Okay. Now, and we did that, and I think we found that to be 117 degrees, if I'm not mistaken. Let me get my pen set up. Okay, so we found angle B to be 117 degrees approximately, okay? I'll put approximately equal, okay? Now, what did we do next? How?
Using the law of sine.
Law of sines, okay. Oh, and here's Josh. And here's, no, you're in J. The J's came in together. Okay. All right. Yes, we did. Which one did you say we did next? C?
Find angle C using the law of
Okay.
sine.
And we use law of sines for that. Law of cosines is a little more involved, more calculations, a little bit more. The law of sines, once you have an angle in the opposite side, or a side in the opposite angle, you can do law of sines. They're easier. They're just ratios. So then we did C using the law of sines, and that gave us, if I'm right, about 41 degrees, right? Okay. Now, law of cosines, law of sines, what do we use for A? No reason, neither one of them. Just you know that the sum of the 3 angles of any triangle, including an obtuse, oblique triangles, doesn't matter, they add up to 180. So just add those 2, subtract it from 180, or take 180, subtract those 2 from it separately, and what do we get angle A to be? 22, approximately 22 degrees. Okay, and it really didn't matter the order on the last 2. You could have done A using the law of sines and then the difference using C. Get C by the difference. It doesn't really matter. But you only need usually to use law of cosines once. Okay, and after that, possibly the law of sines, and then at some point, just the sum of the angles. All right, good deal. There was also the checkpoint there. I highly recommend you do that. Okay. Now remember also the law of cosines has two forms. You're either looking for, like in this case, any one of three angles, so then you'll use the form that's the cosine of the angle, biggest angle generally, and then you do the ratio that gives you that. If you had the side angle side, which is the other condition that we would use law of cosine on, then you usually go for that remaining side first, and then you can use the law of sines. And on that one, it's that side, whatever side you're looking for, squared. Remember, the law of cosines, everything squared, well, not everything, but a lot of things are squared, is equal to the other two squared, sum of the other two squared, minus 2 times the product of the other two times the cosine of the angle in between. So, and there it doesn't matter which one you go for. Well, it's almost, you are going for the side you don't know. All right, I think we're ready for example 2 then. So here's how they did it. And like I said, one of two ways to do the law of cosine. This is if you're looking for the angle, which of course we would be, and you pick the largest angle, and it's cosine B. Now this letter B is only going to show up once over here as a small b. So it's a squared plus c squared minus the b squared, that letter there, divided by 2 times a times c. Okay. So even though these aren't squared, they're multiplied together, so it's effectively a square. Okay. And which is good, which you need, because you see these are dimension quantities. This would be feet squared, feet squared, feet squared. Those all have to be the same. This has got to be feet squared, so that's why it's a times c, which is also feet squared. So the units cancel out because your cosine can't have a unit. You have a perfect pure ratio. Okay, and that gives you the cosine of b. And in this case, that of course gives you, in this case, a negative number, which means you're in the second quadrant. Because cosine is negative, it has to be obtuse angle, and they get a 116.80, which, how can they get 5 digits of precision when nothing had more than 2? So I said the best you can probably do is 117. And at that point, it's much simpler to use law of sines, because now you have an angle in the opposite side, and go to town with that. They did sine A first, we did C, it didn't matter. And they got A to B acute. And you see, there's the other issue. As long as you do that biggest angle first, you know the other two angles have to be acute. So you don't have any ambiguity here. Well, do I take the angle that's the first quadrant angle or the second quadrant angle? Because sine is positive in both of those. Once you do the biggest angle first, the law of sines will give you acute angle, whichever one you choose. Okay? So that gave you about 22 degrees. And then to get C is just the difference of those two and 180, which is about 41 degrees. All right. Enough said. Now, here they're going over the same stuff again. Do you see why it was wise to find the largest angle first in example 1? Knowing the cosine of an angle, you can determine whether the angle is acute or obtuse. See, with sine, it's not clear, because in first and second quadrant, sine is positive. So you can never tell. Are you talking about the acute angle or the obtuse angle? With cosine, it's obvious, because if cosine is positive, that means you're in the first quadrant, it's an acute angle. If it's negative, like our example was, you have to be in the second quadrant, it has to be obtuse. And if you choose the biggest angle first, the other two have to be acute. You can't have two obtuse angles in the same triangle. It just doesn't happen. You can't add the 180 with that. So in example 1, once you found the angle B was obtuse, you knew the other two were acute. But it didn't matter. Even if angle B, as long as angle B was your biggest angle, the other two are always acute. Always, okay, if it's a triangle. Okay. Furthermore, if the largest angle is acute, then the remaining two are also acute. So why make a big deal about it? Go to the biggest first, and you know the other two are acute angles. All right, they're skipping to applications. They're skipping example 2. So let's go back and do example 2. All right. And example 2, you can see larsonprecalculus.com for an interactive version of that type of an example. It says, find the remaining angles and side of the triangle shown below. And let me see if I can do a reasonable rendition of that triangle. Here's the baseline, and we'll call that 12 meters. And they name it C for you. Okay, so we remove all doubt there. Then we'll have an acute angle here, 25 degrees. And we'll have B over here equal 9 meters. Okay, now my 9 meters looks almost as long as my C, so I'm going to make C a little bit longer there. Look about right? Okay. All right. They named this angle A, the one that's 25. Name this angle C because it's opposite side C. We'll name this side over here little a because it's opposite capital A, angle A. We'll name this capital B because it's opposite little b. Okay. So, we know side, angle, side. No way we could use law of sines. Why? Okay, but if you had these two sides of an angle, you could still use law of sines. Why can't you use one here? Second?
This side angle side.
Okay, yeah, you're right. Here's the deal. You don't have the ratio you need. For a law of sines, you've got to know one ratio. A side and the angle and its opposite side. You've got to know that. Otherwise, you can't use law of sines. With the angle being in between the two sides, you don't have a ratio. So you have to use law of cosines on this. Okay? So, and this one says you already know, you know the triangle exists. There it is. Okay? So you don't have any ambiguity here. How would you proceed? What do we look for first? We really only have one choice. Can't quite do that. Law of cosines only uses one angle. So we got to use the one we know. Okay, yeah, if you know the three sides, then go for the biggest angle. But if you know an angle, you're stuck with law of cosines. You have to go for the side opposite that angle. Okay? So that is a squared. And remember, law of cosines, everything is multiplied by another side, either itself or another side. And what would a squared be? Help me.
A squared equals 9 squared.
Okay, b squared plus c squared minus 2 bc cosine a. Got it. Okay, so this would be like you were already doing. 9 squared, which would be 81. I won't put the units, but it's squared meters. Plus, I can do that one too. 144. That would be square meters too. Minus, see, can I do this? 2 times 9 times 12 is 108. And twice that is 216. Times the cosine of 25 degrees. All right. So that should be what a squared is. So someone with a calculator, because I can't do cosine 25 in my head, so go on and do this one. You can just plug in the numbers and do them as it says. You don't have to do it in your head. But anyway, 181 plus 144 minus 216 times the cosine of 25. What does that give you? Anybody? Second?
29.2375.
2375 or something like that. It doesn't matter. Whatever that number is, keep it on your screen and take a square root of it. Because we're not really interested in what a squared is. We want to know what a is. Then what would a be? Something greater than 5? 5.4. Okay, let's just call that approximately 5. Okay? Because the others, you don't have any decimals on those either. So we say approximately 5. But don't lose that number, okay? Because the next thing we're going to do is what? What's your next step? Still got two angles to find, don't we? How do we get those? You could, if you like to work really hard. All right, if you're lazy, yeah, use law of sines. How do you use that? Okay, that number you just got, and that's why I said don't erase it. That 5 point blah, blah, blah over, how does law of sines go? Of sine of 25 degrees is equal to, and you choose which angle you want to deal with. Which one? Okay, 12 over the sine of C. Okay, we don't know C, so that's what we're going for. Okay, so this tells us that the sine C is equal to, do your cross product here, 12 times the sine of 25 degrees. I can't write. My pen is slow. Okay, ooh, that looks like an 8, doesn't it? That's awful. Okay, 25 degrees divided by 5. Or 5 point blah, 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 whatever you got there. Okay? So, in doing the calculations, use as many decimals as you can keep. Okay? When you're writing your answer down, that's when you round it off. Okay? So, using all those decimals that you had, 12 times. What I would do on this one, since I had that on the screen, I would do the reciprocal of that, which is 1 over x here, x is minus 1 key, with that number, then multiply that by 12 times the sine of 25. Be sure you're in degree mode, by the way. And what do you get sine C to be? Blah, 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 blah. Okay. Then, while you've got that on the screen, do what? Arc sine or inverse sine. And that gives you C as approximately 69? Okay, let's call it about 70 degrees. Okay? Because the other one was only given the 2 digits. Okay. For the angle B, do we use law of cosines, law of sines, or? Yeah, just add them up and see what you get. So if this is 70 degrees, it looks reasonable. That seems like a bigger angle than 70 degrees, so they may not have drawn it well. I was copying them. And 70 and 25 would be 95. And subtract that from 180. 85. That's not right. There's something wrong here. Why do I say that's not right? Because the biggest side is opposite your middle angle, and your biggest angle is opposite your middle side. So evidently we used the wrong one. If C was 70, that was when C was on this side. Do it on this side. So this is, remember, the sine can be first or second quadrant. 70 would be here. What would be the possibility here? This is 20 degrees short of 90, so do 20 degrees past 90, and what do you get?
Degrees.
110 degrees. So our C should be 110 degrees. So you see, always keep the mind open there of what you're doing. And it looked at first like the picture may have been wrong, but then when we saw that the other side gave you a bigger angle, you know it's not just the picture, you chose the wrong angle. So that would be 110 and 25 would be 135. Subtract that from 180 and you get, what, 45? That actually looks like that could be close to true. Because 25 and 45 would be 70, yeah, plus 110. Okay. So here, this example, that would lead me to suggest, in this case, once you found what A is, then go with the smaller B, because you know that's got to be acute. Just drawing that, it looked like that was obtuse, so we should have even been guessing that. In this case, I'm going to go for the smaller angle. And that way you know it's going to be acute, so you don't have to fiddle with that, then that'll be whatever's left. So that's not a bad thing. I don't think they make a point of it. Let's see what they got. I rounded to 5, and if you kept that round in there, you may have gotten off a little bit on your degrees. But they went with angle B next, which is a good move. And they got that to be 45 degrees, about 44.7. So we still were right in the ballpark, and the other being one. Oh, how silly. If you go for the smaller angle, they went through and said it could be either way. No, it can't. This is the longest side. That's the largest angle. You go for this one, you know it's got to be acute. It can't help but be acute. So therefore, go for that, and then don't even worry about the other possibility. It's not going to happen. This will be the acute angle. And that can wind up being obtuse if you want it. I mean, if it turns out being that. So in that case, I would definitely have done that and not worried like they did about whether B1 and B2. No, you don't have to worry about that. Just do go for the smaller angle, or the angle opposite the middle side or the smaller side. You know it's got to be an acute angle. Only the side opposite the largest, the angle opposite the largest side can possibly be obtuse. Okay, so they did some extra worry for nothing. All right. All right, any questions on that? So side C was not 70, it was 110. Now the other way to get that, rather than doing like I did, 70 was 20 short, so do 20 over, just subtract 70 from 180 and you get 110. That's another easy way to do it. So C had to be 110. It could have been either one, but if you had gone for B first, you knew that had to be acute. Okay. All right, now I think we're ready for applications. Any questions before we leave it? Anybody? Bless you. All right, here's the application. The pitcher's mound on a women's softball field is 43 feet from home plate, and the distance between the bases is 60 feet, as shown here. And they note the pitcher's mound is not halfway between home plate and second base. It's a little further back, which means you don't have a right angle in that triangle. Okay? How far is the pitcher's mound from first base? Now, here are the things they do let you know. This is not a diamond, though they call it a diamond. It's actually a square. I guess you could say that's a diamond. This is a square. These are 90 degrees between each base. Okay? And if they are 90 degrees, and the pitcher's mound, even though it's further back, it's still in line with second base, so that has to be at 45 degrees. Okay? Because it's half of 90. This is not 45 here because pitcher's mound is further back. Okay. Now what they do tell you is distance from home plate to pitcher's mound is 43 feet, and from first to home plate to first base is 60 feet. All the bases are 60 feet. Okay. How far is the pitcher's mound for first base? Now, tell me, Jake, is that also true in baseball? Is the pitcher's mound a little further back, or is it right dead on?
I think it's a little further back.
Yeah, I thought it probably was too. Okay. I knew in softball, women's softball, it was that. Okay. Now, I think your base paths are more than 60, aren't they? Or at least 90, I thought so. Okay. All right. And so, therefore, the pitcher's mound is more than 43 feet. Thank you very much. Okay. That would be terrible to have a fastball pitcher throwing at you from 43 feet away. That would be awful. Okay. And of course, center field is way back there. Okay, but never mind. All right. So, how far is the pitcher's mound from first base? What we're looking for is H, the way they've drawn it here. There's your unknown. What can we use to get it? You can't use right angle trig. There's not a right angle in that triangle. Law of cosine is the only possibility because what you have is a side angle sine, just like we said before. But law of cosine gives it to you directly. And what would that be then? Well, sort of indirectly. What does it give you? Yeah. Okay, it's, yeah. And that's h squared is what this tells you. Sorry, it'll come back, I think. Okay. What did you say now? 43 squared plus, which is 3,600. I can do that in my head. What next? Minus 2 times that. Can I do that in my head? I'm not sure. Well, let's just write it out. 2 times 43 times 60 times what?
Cosine
45 degrees. And we actually know what that is. It's root 2 over 2. So if you didn't want to even use the cosine key, you could do that. Okay? So however you want to do it. 48 squared plus 3,600 minus 2 times 43, and I would do times 60 times the square root of 2. But you don't have to do that if you don't want to. Do however you want to. You'll get h squared, which is going to be a pretty good sized number. Anyone got it yet?
H squared is 1,800.33.
0.33? Wow, I didn't know it would come out that. So what do we do with that? Square root of it, and you get h is equal to 40 something. 46.43? 42 point. Nah. Oh no, you're right. 42.43. So I'm just going to say approximately 42 feet. Okay. I was looking at that and thinking that's the longer side than this, but it's not. I don't think. Yeah, this is longer than that, according to the picture, but also according to the angles. Because this is a 45 here, this is greater than 45 here, so this has to be less. So about 42 feet. They probably give it a lot more thing. 42.43 feet is what they say. I just don't see how they got the precision to do that, but whatever. Closer to maybe the 44.5 feet, so you could say that. And by the way, there's a checkpoint after every one of these examples. Really a good idea to do those. So let's see how they proceed with this one. In the triangle HPF, which is home pitcher first, the H is 45 degrees. The home plate, the angle between home plate and pitcher is 45 because it exactly bisects the right angle at home plate. The F on the distance from opposite first base, which is distance from home to the pitcher's mound, 43 feet, and the P, which is the base path opposite the pitcher's mound, that's 60 feet. They gave us that. So using law of cosines for this sassy case, side angle side case here, you have H squared is equal to F squared plus P squared minus 2FP times the cosine of H, which comes out being 43 squared plus 60 squared minus 2 times 43 times 60 times cosine of 45, which we know, and they say that's about 1800.3. In the book they said 0.3290, however. Okay. So the approximate distance from that is the square root of that, and that would be close to 42 feet, a little bit more, closer to 42 and a half feet. Okay. There, Skippy. Sorry. Sorry, my head is clogging up. The first class I had this morning was in a room that was boiling hot. I mean, it was just miserable in there. And I think that's got my head completely dried out. Okay. Now, and if you remember me griping before, before it turned cold outside, that room was freezing, okay? And this room was comfortable. Now that room is way too hot, and this room is still comfortable. So I wish we were all in here. I didn't have to go back and forth. Okay. So we're doing example 4 at the bottom of page 411 in section 6.2 in chapter 6, of course. An application of the law of cosines, a ship travels 60 miles due north. So they're starting down here from point A. Yeah. Starting from point A and going 60 miles due north. Okay. And they're saying that's to point B. Then adjust its course is shown in the figure, which they don't show, thank you very much, and they travel another 80 miles in that new direction. They didn't tell you what direction that was, so they shift and go 80 miles in this new direction, which they didn't tell us what it was. Okay? After traveling that 80 miles in the new direction, the ship is 139 miles from home. So that's going to be B here, this is C up here, and we know this distance is 139 miles. Not a very pretty picture, but get over it. Okay. Describe the bearing from point B to C. We want that angle right there, the bearing from B to C. Okay. Now, what might we try to use? What do we have in our oblique triangle here? A side, and a side. The SSS case, which is not a very popular abbreviation. So what's the only technique we have for that? Law of cosines. It's the only thing that would do 3 sides. And where would we normally start with the law of cosines? If you have 3 sides. 2 examples back. The biggest angle, which happens to be which? Obviously, B, one opposite the longest side. Which is good because that's the angle we're interested in. But law of cosines is going to give us this angle, not that angle. But how are they related?
It's complement angle.
Supplement, yeah, supplement. Okay, so we're going to find angle B using the law of cosines. And how does that go? And even if we're looking for one of the other angles, we'd still have to go for B first. So what would that be? What were you going to say? Cosine of capital B is equal to A squared Oh, okay, you said 80 squared. I thought you said A squared. I was thinking, why are you going to say that? But I went along with it. Okay. 80 squared plus...
80 squared plus 60 squared.
Yes, plus 60 squared minus 2 times... No, you're right. Yeah, sorry. I was doing the wrong one. Well, yuck. Okay. Minus 139 squared divided by 80 times 60. Doesn't matter the order, bless you. I'm coughing, you're sneezing. Have a merry old time here. All right. So you got the math, you got the calculators, do it. Now that is an 80 there, it's not 89. That's misleading. Let me erase and copy it over. It's 80. Ah, okay, that's a 0. Negative what? I couldn't hear.
Negative
0.97. Blah, blah, blah. Okay. With that on the screen, do a what? Yeah, arc cosine. Okay. Inverse cosine. And B would become pretty good sized angle, isn't it? 166. Okay, let's just leave it 166 degrees. And then that gives you this 166 degrees. But what do you do from there? That's not what they're asking for. Huh? Yes, from 180. Okay. And that gives you 14 degrees. Yay? Okay, and so that would be what they asked for, if I can find it again. Describe the bearing from point B to point C. Remember how we did our bearings? From B to C. You first look either north or south. This way you'd have to be looking north. So you do north, 14 degrees. Which way did you go from north? West. North, 14 degrees west. And they did 13.86 degrees west. I don't see how they get that kind of precision, but you get the general idea. And if you're out over the water, that's as good as you can do anyway. I've never seen a compass face that you could read to the nearest hundredth of a degree. Okay. Make sense? All right, there is a checkpoint there. I highly recommend you do the checkpoints. Okay. So any questions on this one or any of these so far? Because now we're going to, just like we did on the last one when we were doing law of sines, we came up with a new formula for calculating the area of a triangle. Okay? It's one that sort of looked like the law of sines formula. Now we're going to do another one. And this looks sort of like a law of cosines type formula, because this time it says the law of cosines can be used to establish the following formula for the area of a triangle. The formula is called Heron's area formula after the Greek mathematician, okay, whatever, Heron, who lived about 100 years BC. Okay. Here is his formula. Given any triangle that you know the lengths. Okay? Now, think about the other two area formulas. The standard one that we always used in high school or whatever was 1/2 the base times the height of the triangle. Guess what? The height of a triangle is a very hard thing to measure. How in the world are you ever going to know that? Okay. So, what we did next, after the law of sines, we did the area of the triangle was AB, 1/2 AB times the sine of the angle C, or something like that. Well, AB, that'd be easy to measure, but figuring the angle between, that's not particularly easy either, okay? But it's probably better than knowing the hypotenuse. I mean, the hypotenuse, the height. A little bit easier. But this one, if you have a triangle, you can take a tape measure and measure the three sides. You don't need to know an angle. You don't need to know the height. All you need is three sides. This is something very practical. Easy to measure the three sides of the triangle. Okay? So let's say those three sides are A, B, and C. Then the area of the triangle is the square root of S times S minus A times S minus B times S minus C. What in the world is S?
A plus B plus C over C.
Okay, why it's named S, it's called the semi-perimeter. Because if you add A plus B plus C, you've got the perimeter, right, of the triangle, and then take half of it. Half of it's semi-perimeter. That's why we call it S. Okay? And so if you know the three sides, calculate the perimeter, take half of that, and then use the formula. Okay? Pretty straightforward. Here is an example using that. Find the area of a triangle having sides of length A equal 43 meters, B is equal to 53 meters, and C is equal to 72 meters. What's the first thing you're going to do? Anybody? Okay, and what is S? What was S? A plus B plus C divided by 2. And then in our case, that's the 43 meters plus 53 meters plus 72 meters divided by 2, which would be 43 and 53 is 96, and 72 is 168, I believe, meters, divided by 2, which would be 84 meters. I'm doing it in my head, so check me and make sure I'm right. All right, we found S. What do we do with that? It's coming back, I think. It's being a pain in the neck. Okay. What do we do with that? And what is that? Okay, the square root of 84 times 84 minus 43 times 84 minus 53 times 72. Okay? And that would be the square root of 84 times, if I could do my math, that's 41 times 31 times 8, no, 12. All right. I won't try to do that multiplication in my head, nor will I take the square root of that in my head. I'll let you figure that out. Calculators, it's pretty straightforward. The square root key, it'll open parentheses, 84 times 41 times 31 times 12, close the parentheses, hit return. What you get?
1131.
Let's make it 32. And that would be square meters. Now wait, let's check on that unit. Okay? Well, 84 was in meters. 84 minus 43 was in meters. And that was in meters, and that was in meters. So this would be meters of meters of meters of meters. That's meters to the fourth power. But when you take the square root of it, you only take the square root of the number. You take the square root of the units as well. And the square root of meters fourth is meters squared. So sure, that's a good measure for an area. So 1132. Okay, they did 0.89 also. All right. Then, excuse me. There is a checkpoint, and I would highly recommend you do the checkpoint. Oh, wait. Let's see how they did the problem. Sorry about that. Forgot. They are going to do it too. Okay? Yes. Because the semi-perimeter is half of the perimeter, we can do 168 divided by 2, which is 84. And using that, Heron's formula is 84 times the difference, times the difference, times the difference. 84 minus 43, minus 53, and minus 72. And then that would be 84 times those, and that's 132, I would say, approximately, square meters. Now, here's what I was going to do. Okay. So like we said, now we have three different formulas for the area of a triangle. The good old standard that you probably know most of your life is 1/2 the base times the height, which is very easy, very straightforward, except in reality, yeah, it's easy to measure the base, but how in the world do you get the height there? Because the height is from the vertex up here, which you sort of know here, but how do you know you're perpendicular down here? It's not an easy thing to know. So that's not particularly easy in a practical sense. In an oblique triangle, which that covers oblique triangles as well, then your form was 1/2 BC times the sine of A, 1/2 AB times the sine of C, 1/2 AC times the sine of B. Any one of them. It was easy to know these two lengths. Getting an angle is not that easy. I mean, you have a huge protractor you put down on the ground to see what it is. You have a section available you could use. If you had, yeah, you can get a very precise measure of that. I just don't have a section on hand, you know. If you're a surveyor, yeah, you would have that on hand. Of course, they're a pain in the neck to set up and all like that, but then you can get that angle very precisely. So that has limitations, finding those angles. The sides are easy. Heron's formula, though, easy to measure each of the three sides. Just get a tape measure. Measure those three sides of the triangle, add them together, get the perimeter, take half of that, get the semi-perimeter, and then use this formula. Okay? And that's pretty, I mean, you need a calculator for sure. You do for the others as well, most of them. But pretty easy to get. Any questions on that? All right, we're at the point of our favorite vocabularies, okay? The standard form of the law of cosines for cosine B is equal to a squared plus c squared minus b squared over 2ac is, I think I know what they're asking for, but my goodness, why is that called the standard form? I think they're asking for the other form. Yeah, they call it standard form and alternative form. And what would that be?
B squared equals a squared plus c squared minus 2 times a times c cosine b.
Got it. That's it, exactly. Okay, number 2. When solving an oblique triangle given 3 sides, use the blank form of the law of cosines to solve for an angle. There they're asking for standard alternative. Yeah, if you know that, 3 sides, then you use the alternative form. They're really big on standard and alternative. I don't know why. Okay? When solving an oblique triangle given 2 sides and their included angle, use the blank form. What's the other one? Standard form, exactly, of law of cosines to solve for remaining side. And number 4, the law of cosines can be used to establish a formula for the area of a triangle called Heron's area formula. Okay, those were pretty straightforward. All right, they big on standard and alternative. Okay, I would do any of the odds 5 through 11. They're all at Calc Chat. 9's at Calc View. Then I would do any of the odds 13 to 23. They're all at Calc Chat. Then I would do any of the odds 25 to 29. They're all at Calc Chat. 25's at Calc View. Then do any of the odds 31 to 35. They're all at Calc Chat. 33's at Calc View. Do any of the odds 37 to 43. They're all at Calc Chat. 37's at Calc View. Then I mentioned surveying. Here's an example of it. Do any of the odds 45 is a surveying one. Baseball's a 47. A length is 49, so you pick any of these you're interested in. Navigation's 51, another surveying 53. Do one of the other, 45 or 53. 55 is a distance one. That would be more like, I don't know, maybe not any of those, but any of the odds through 59. Okay, some of those are just purely geometry. Then there's under exploration, number 61 is a true-false. This should be at Calc Chat. There's a think about it, 63. You can think about doing it if you'd like. That should be at Calc Chat. And then there's a writing on 65 if you want to look into that. 67 is a proof if you want to look into that one as well. All right. Now, that finishes the first part, which is oblique triangles, basically. All right. Now we're moving to sort of another additional topic in trigonometry. Okay? And why my thing didn't show up, I don't know, but here we're having to do through it again. Now we're going to 6.3. Now, I'm assuming that most of you are pre-engineering majors, is that right? Okay. If you are, you're going to physics sometime soon, okay? Probably after Cal 1, if you're pre-engineering. Now, if you're not pre-engineering and maybe something like physical therapy or something like that, you may be going straight to physics, college physics, which is trig-based rather than calculus-based. But whichever physics you're going to, if you're going to a physics, which I assume that most of you are, you will be, we're still in chapter 6, additional topics in trigonometry. Now we're going to discuss vectors in the plane. And physics uses vectors all the time. Other places use them too, but certainly physics uses them all the time. So this is something you'll be running into a lot. So we'll represent vectors as directed line segments. We'll write component forms of vectors, which is the best way to write a vector. We'll perform basic vector operations that represent them graphically. Just performing them is easier. And write vectors as linear combinations of unit vectors, which is a pretty straightforward procedure as well. And we'll find the direction angles of vectors, and we'll use vectors to model and solve some real-life type problems. Okay, so let's start off. What in the world do we mean by vector? There are quantities you'll deal with in physics or otherwise that are just numbers, like your mass or the mass of anything. Just a number, okay? Time is just a number, okay? Energy is a number, okay? Lots of things are just numerical quantities. But there's a lot of other things that are more than just a numerical quantity. A displacement as opposed to a distance. A distance is a number. A displacement is indicating not just how far you moved, but how far in what direction you moved, okay? Similarly, speed is how fast you're going. Velocity is how fast you're going in a given direction. Now, in everyday language, we use speed and velocity interchangeably. In physics, however, velocity is a vector quantity, speed is just a scalar quantity, which is the magnitude of your velocity vector. Later, then you'll do accelerations, which is in a direction. That is a vector quantity. Once you have acceleration, force depends on acceleration. It's a vector quantity. And sure, forces have to be directed, okay? I can push down on the chair here and not do much to the chair. I'm mostly hurting my thumb, okay? But if I push the same force this way, I'm moving the chair. So, same force, different directions. So forces are directions. Same magnitude of force, different directions. So forces are vectors, okay? Momentum is a quantity that's a vector. Force and velocity, anything that's a vector, has both a magnitude, which time and mass have too, but they also have a direction. They cannot be completely characterized by just a number. You have to have a number in a given direction. To represent such a quantity, we use a directed line segment, such as this, and here's what we mean by that. Directed means it's going in a given direction. This line segment is different from that, okay? Because this one's going from P to Q, going from Q to P. Even though it's the same length, it's a different direction, okay? So when we talk about a directed line segment, okay, it has a given direction. And what makes it a line segment as opposed to a line? A line is infinite. A half line is infinite, okay? That's also called an array. So neither of those. A line segment, though, is a fixed length. That's your magnitude. The direction is your direction. So there we have both of the quantities. Now, when we name this, if this is vector PQ, just by that name, and notice they will also put the arrow over it. That indicates it's not just two letters written next to it. That means it's a vector. That means P is the initial point and Q is the terminal point, meaning it points from P to Q and points from P to Q. See, that illustrates that. Even if Q is in this direction, we don't change it. You know, it's initial point P, terminal point Q. Okay? Terminates there, ends there. That's the direction your arrow is going. Okay. So that's one way to represent a vector quantity, a directed line segment. The directed line segment PQ has an initial point P, terminal point Q. We just said those. Its magnitude or its length is denoted by the double bars here. Now, the double bars to me look a lot like a double absolute value. And the concept of absolute value is important because the magnitude of a vector is never negative. Just like absolute value of a number is never negative, the magnitude of a vector is never negative. Its magnitude or its length is always a positive quantity. And you find that using the distance formula. The square root of the difference between your components of that, and we'll get to that later, your x2 minus x1 squared, y2 minus y1 squared, square root of that. Or three-dimensional you have z minus z1. Two directed line segments that have the same magnitude and the same direction are what we call equivalent, and later we'll actually call them equal. So all of these line segments, as long as they're in the same direction and same magnitude, those are equivalent vectors. And in fact, that means you can pick up this vector and move it anywhere in the plane, as long as you keep its magnitude and its direction exactly the same, that vector can be represented anywhere on the plane. Okay? So those are all equivalent to each other. And we say they're equal to each other. Now, if one of these pointed in a different direction, no. It has to go in the same direction as well as magnitude. Certainly if it went out in some other direction, even though it has the same magnitude, different vectors, not equivalent. Okay. By the way, folks, I forgot to bring my watch in today. It's down in my jacket pocket. I forgot to take it out and put it in this pocket. So y'all will let me know.
We got 5 minutes.
5 minutes? Okay. I was afraid y'all would just let me go on forever. I know Caleb would. He doesn't mind me talking for a long time. So the set of all directed line segments that are equivalent to the directed line segment PQ is called the vector V in the plane. That's a weird way to express it, but vector V would be represented by PQ, where its initial point P, terminal point Q, now any vector that's equivalent to that, whether it's over here, or wherever, okay, as long as it has the same magnitude and direction. Vectors are denoted by lowercase, boldface letters such as U, V, W. Guess what, team? I can't write boldface. So when I write a vector, I will put the little arrow over the top, a lot like PQ has. So I would, let me get my color back. Okay? I would write this as vector V, or vector U, or vector W. I put the little arrow over the top, meaning that means it's boldface, that means it's a vector. Because I can't write boldface, and you know what I'm talking about. Okay? Now, here's example 1. Show that U and V in this figure are equivalent. And you can't say, oh, they look like they're parallel. They look to be about the same length. That won't cut it. You have to show they are indeed equivalent. What would it take for them to be equivalent? Same magnitude and same direction. Can anyone remind me how we calculate the magnitude of these vectors? Hint?
And you subtract the 1
Okay.
4
Squared plus 1 minus, or 2 minus 4 squared. Okay? You could have said 4 minus 1 squared and 4 minus 2 squared as long as you keep the order the same. Because guess what? When you square them, it doesn't matter whether they're positive or negative. Okay, so that's going to work. So this would be the square root of 3 squared plus 2 squared, which would be the square root of 9 plus 4, which is the square root of 13. Okay, there's RS magnitude. Let's do magnitude of PQ. Same way, what would that be? Help me, somebody.
square root of 0 minus 3 plus 0 minus 2 squared.
Okay, and as a cursory observation, that's the square root of 3 squared plus 2 squared, which is exactly the same as this one, so it's going to come out the same square root of 13. So they have the same length, therefore they're parallel? Therefore they're equivalent?
Yeah.
Nah, got to be the same direction as well. How do we determine that?
Where the arrow is pointing.
Say again?
Where the arrow is pointing.
Okay, well, that's generally, but you see, what if they were just off a little bit?
See if they're parallel.
Okay, how do you guarantee they're parallel? If they're parallel, what would be the same?
Slope.
Slopes are the same, and what would be the slope? So let's do the slope for RS. What would that be? Say again?
2 over 3.
2 over 3. You're right. 4 minus 2 over 4 minus, so what's the slope of PQ?
That would be 3 over 2.
Really?
2 over 3.
Say again?
Same thing.
Same thing, 2 over 3. Rise over run. The row's 2 and run 3, right? The change in y's is 2 and the change in x is 3. Just like you did before. It's 2/3 also. So once you know they have the same slope and same magnitude, yep, they're equivalent vectors. Got it? Or disagree? Okay with it?
With it.
How did you get 2 over 3 up here? Did you do 4 minus 2, rise, over 4 minus 1, 3? So here you do 2 minus 0, rise, 3 minus 0, 2 over 3, right?
But if you're rising it, would that not be the y value, not the x value?
Yeah, the y is 2.
Oh, my bad.
Yeah, okay. Earth to Dawson, come in please. Okay, all right. No, exactly right. Okay, so there was example 1. They have the same slope, same magnitude, so they are the same vectors. We will begin next time on component form of a vector, which is the way to go on vectors. Let's see if we got enough for you to do any homework exercises here. We've barely got started, but I think we probably got something that you could do. I think you can do number 9 for sure. And you can do any of the, either 11 or 13 for sure. But all those are at, the odds are at Calc Chat, 11's at Calc View. And we'll stop there and pick up the rest of those later. Okay. Good deal. One other assignment. This is pretty major, folks. Have a great Thanksgiving. All right. Good deal. I would say don't eat too much turkey, but eat as much as you want to, as long as you get it slept off before Tuesday, okay? After Thanksgiving. Have a good one.